Hi guys, Miss Gatos here. Just wanted to create this video to help you guys summarize the effects of h, k, a, and b on our transformed function. It will also help answer that question of when I move a graph to the left 4, why isn't it x minus 4? And if I stretch something horizontally by a factor of 3, why isn't b value 3 in the equation? So I'm hoping that this video will kind of answer all of those questions. So let's get going with vertical translations. So vertical translation is an up and down movement. So since I am moving up and down, it is only going to impact my y values. So let's look at an example here. If I'm going to look at moving a graph y equals x squared, a nice base quadratic graph from 20-1, and I want to move it 5 units up. That means I want to take all of my xy points on y equals x squared, and I want to move them all up 5 points, 5 units. So you can see the y values are the only thing that's changed. X stays the same. So let's look at my equation. If I were to take this equation and move all my y values up, so I have a y equal, and what are all the y values? All of the y values are found by taking x and squaring it. So since I want to move all of my y values up, I can just add on a 5 there. So y equals x squared plus 5 would be the base graph x squared moved up 5 units. Now let's try that for down. So I want to take the same graph, but this time I want to move it down 5 units. So since it is a vertical translation, again, my mapping notation, x stays the same, and all my y values are going down 5. So back to my equation, y values are being impacted, and I have a y equals equation. So I'm going to take all of my y values, which is x squared, and I'm going to move them down 5. So x squared minus 5 should move the graph down 5. So I always like to check things or verify things graphically. So let's look at that and see if our equations are right. I want to know, does this actually go up 5 units? Does this actually go down 5 units? So if we look at on our calculator, I have my base function, and that's graphed in black in the middle there. And then I have the first one that I did where I went up 5 units. So you can see that yes, just looking at the vertex, I went up 5 units. So the plus 5 there works to go up 5. And then on this graph, I want to check, did I go down 5 units? So here's the base function, and this time I'm going down 5 units. So by subtracting 5 on the outside, I see that that works. So in general, here's what it's going to look like. If I have any function graph at all, and I do plus k, the graph will move up k units. If I do minus k, the graph will move k units down. So we're going to take this same idea, and we're now going to look at horizontal. So horizontal translations, moving functions left or right. When I move functions left or right, this will only impact my x values. So moving left and right only changes x. Y stays the same. So let's look at this graph here. Again, the base function, y equals x squared, I want to move it 5 units to the right. So what that means is I'm taking all of my x values and I'm moving them 5 to the right. My y values stay the same. Now, what happens here is that we have a y equals equation. And if I want to do something to x, such as moving it right, I need an x equals equation. So I can't do anything to x if I have a y equals equation. So I'm going to get an x equals equation. So to get rid of a squared, I'm going to square root both sides. Remember, when you take the square root, it's going to be plus or minus. So I'm going to, by taking the square root, I'm going to have that x is equal to plus or minus the root of y. Let me just write it like this. X equals plus or minus the root of y. So now I know what x is. So I have an x equals equation, and x is found by taking positive and negative the square root of y. So if I now want to move 5 units to the right, that means I want to make all of my x values 5 units bigger. So I'm just going to add 5. Okay, now I have an x equals equation here, but I really want for my final answer to have a y equals equation. So what I need to do is change this x equals equation to a y equals equation. So I have x equals plus or minus root y plus 5. So let's get y by itself. I'm going to subtract 5 from both sides. And then to get rid of a positive and negative root, I'm just going to square both sides. So I end up with x minus 5 squared equals, well, positive y squared and negative y squared are both just y. So now I have a y equals equation. So you can see here with my equation, by going 5 units to the right, my equation becomes x minus 5 all squared. A little bit different than what we were expecting, but you can see now why that works. So 5 units right, I have an x minus 5 equation. So we're going to do the same thing, but now we're going to go 5 units to the left. So moving 5 units to the left, let's look. So again, I have a y equals equation. If I'm moving 5 units to the left, that means all of my x values will be 5 less. So I'm going to just subtract 5 from all my x values, my y values stay the same. So again, since I'm doing something to x, I need an x equals equation. And I showed you on the last slide how we came up with an x equals equation. So I can just write that down again. I don't need to show you that again. X equals plus or minus root y. So if I'm moving the x values left 5 units, and this represents all of the x values. So to find the x values, I take positive and negative square root of y. And I'm going to subtract 5 because that's what I'm doing to make all of my x values go to the left 5. So here's my equation, plus or minus the root of y minus 5. But again, we want a y equals equation. So I'm just going to add 5 to both sides. That's gone. So I get x plus 5 equals plus or minus the root of 5. The root of y. And to get rid of y, I will just square both sides. So I end up with x plus 5 all squared equals to positive root y and negative root y squared are both just y. So you can see, moving 5 units to the left, I actually end up with x plus 5 all squared. Okay? So let's just verify this on the calculator. So the very first equation that we did, the x plus 5 equation, we were doing that when we wanted to move all of our points 5 to the left. So let's just see. Here's my base function. Look at the vertex. And plus 5, you can see, does in fact move it 5 to the left. And this one was when we went 5 to the right. Okay, so x minus 5, that's in blue. And you can see that that graph has also moved in the correct direction. So you've seen algebraically why it's the opposite, and we're verifying that graphically. So let's put that together now. If I have y equals f of x plus h, so the plus h, the graph moves h units to the left. If I have x minus h, the graph actually moves h units to the right. So I hope that answers the question as to why left and right are the opposite signs of what you would expect. Let's look at stretches, the same idea. So stretching something by a factor of 5 with respect to the x-axis. This is a vertical stretch. So if I'm doing a vertical stretch, I am stretching away from the x-axis. So I'm stretching away from the x-axis. And that is going to only impact y values. So in terms of my mapping notation, all of my x, y values are going to become x, a, y values. Okay? Or in this case here, I'm stretching it by a factor of 5. They're all just going to be 5 times bigger. Okay? So let's go to our equation, y equals x squared. Now I'm stretching these by a factor of 5. So I'm taking all of my y values and making them 5 times bigger. Well, since y equals x squared, all of my y values can be found by taking an x value and squaring it. So since these are my y values and I want to make them 5 times bigger, I just do 5 times all of my y values, or 5x squared. So this equation should be a vertical stretch by a factor of 5. Let's try something a little different. Let's try by a factor of a 5th. Okay, so again, I'm going to take all of my x, y points on y equals x squared. X values stay the same, and my y values will now be 1/5 of what they were before. Okay, so let's look at what this looks like in the equation. So I have y equals x squared. These are, again, all of my y values. Okay, so y values are found by taking x and squaring it. So since I want to make all of my y values 1/5, I just multiply it by 1/5. So you've seen this algebraically. Let's just look graphically and see if that worked. So again, here's my base function. And the first thing that we did was a vertical stretch by a factor of 5. So you can see my base function here. All of these points here became 5 times further from the x-axis. So see this point here, you can see the distance that it is from the x-axis. I'm going to stretch it and make it 5 times bigger. So all of those points were made 5 times bigger. So imagine it's kind of like I pulled the parabola by the ends and made it 5 times taller. So it is a narrower graph. Now this one was a vertical stretch by a factor of 1/5. So all of these points on the parabola were made 1/5 the distance from the x-axis. So for example, this point here was made 1/5 the distance to be here. So it's much closer. So every one of these points, like this point here, made 1/5 the distance is here. So this is going to produce a much wider graph because it's kind of like taking the parabola and making it 1/5 its size. So it looks like it worked out nicely. So to summarize, if I have a times f of x, a is the vertical stretch. So it has been vertically stretched with respect to the x-axis by a factor of a. So now let's do the same thing but horizontal. Okay, so same parabola, y equals x squared, and I'm going to horizontally stretch it by a factor of 5 with respect to the y-axis. So this time I'm looking at the y-axis, and I'm looking at stretching it away and towards the y-axis. So stretching away and towards the y-axis is going to impact your x values. So if I want to take this graph and I want to horizontally stretch it by a factor of 5, what that means is I want to make all of my x values 5 times further from the y-axis than they already are. So x values are impacted, y values stay the same. So since I'm changing my x values, again, I want that x equals equation, which we already saw was plus or minus the root of 5. So what I want to do is I want to look at stretching this by a factor of 5. So I want to make all of my x values 5 times bigger. So 5 times bigger, like that. There's all my x values, and I'm going to make them 5 times bigger. So again, I want a y equals equation. So I've got to rewrite this now as a y equals equation. All of our functions are y equals equations. So to get y by itself, I will divide both sides by 5. So that's gone. So x divided by 5 is the same as 1/5 x equals plus or minus the root of y. So to get y by itself, since I've square rooted it, I will square both sides. Okay? So here I just have 1/5 x all squared equals to the square root of y, and negative root of y is just y. So I end up with y equals 1/5 x squared. So you can see, stretching it horizontally by a factor of 5, my b value here actually ends up being 1/5. So reciprocal relationship there. Let's see what happens when I do this horizontally by a factor of 1/5. Okay, so again, horizontal stretch by a factor of 1/5 with respect to the y-axis. So my mapping notation, all of my x values will be 1/5 the size. Okay, so since I'm only impacting my x values, I want to go back to that x value, or that x equals equation. And I want to make them all 1/5 the size. So I multiply all of my x values by 1/5. So they are now 1/5 the size. So I want, again, a y equals equation. So to get rid of a dividing by 1/5, or multiplying by 1/5, or dividing by 5, I will multiply both sides of the equation by 5, because 1/5 of 5 is 1. So I end up with 5x equals 2 plus or minus the root of y. And again, to get rid of the square root, I will square both sides. So 5x all squared equals root y squared, or negative root y squared is just y. So you can see that if I have horizontally stretched it by a factor of 1/5, my b value becomes a 5. So let's put that together and just check to see if our equations are in fact correct graphically. So again, here is my base function. So we had, the last example we did was 5x all squared, and we said that was a horizontal stretch by a factor of 1/5. So you can see all of these x values are 1/5 the distance from the y-axis. You see they come in and they hug it, and they become quite narrow. Versus this one here, y equals 1/5 x squared. This we said was a horizontal stretch by a factor of 5. And you can see all of these x points here become 5 times further from the y-axis than they were originally, making it much wider. So what that means is it is a reciprocal relationship. So in general, if I have y equals to f of bx, it has been horizontally stretched with respect to the y-axis by a factor of 1/b. So hopefully that will help explain to you why everything is kind of opposite of what you would think horizontally. So I just want to end with comparing them one last time here, putting it all together. So this is our transformed notation, y equals a f of b x minus h plus k. So on the outside, a and k, those affect your y values. So see how it kind of makes a big capital letter Y? It impacts your y values. A is your vertical stretch, and K is your vertical translation. We saw in the past two examples that vertically, both stretching and translating, exactly the effect you'd expect. So if A is 4, vertical stretch by a factor of 4. If K is -3, vertical translation down 3. However, on the inside, when I look at B and H, these impact my x values. So I have an x in there to show that they impact x values, where B was our horizontal stretch and H was our horizontal translation. Now, this x, showing you that it impacts x values, can also mean that they kind of interchange. They're opposite of what you would think. So these are the opposite effect of what you'd expect. So for example, if B was 3, it would be a horizontal stretch of 1/3. If B was 1/2, it would be a horizontal stretch of 2/1 or 2. Same thing with your horizontal translation. If it's x minus 3, you would expect that it goes 3 to the left, but it actually goes 3 to the right. If it was x plus 7, the plus 7 you would think goes to the right, but it actually goes to the left. So I hope that this video explains to you adequately why horizontally works out a little differently than vertically, and that it was a good review.